The name of this lesson is Polyhedra and Cross Sections. We want to be able to correctly identify a polyhedra based on its component parts, as well as be able to describe the polygon that results from the intersection of this three-dimensional figure and a plane. Okay, so polyhedron, which is the plural for polyhedra, it's a three-dimensional solid that has the following properties. It's composed entirely of polygons. Okay, the sides are the faces, so each of the polygons is called a face, or like the sides, like this would be one face. Okay, and so that one is a triangle. In class, I have a lot of samples of these, and if you're able to look on with Skype today, maybe you can see those, but there are samples around that you could look for. Okay, this segment where two polygons intersect is known as an edge. So like, let me change this color. So this is an edge, and that's the intersection of that blue and this green, and so all of these are edges. Okay, so where the polygons intersect are the edges, and the point where three or more intersect is a vertice. So right here, right here, right here, and etc. So we have faces, edges, and vertices. Okay, polyhedra are named according to the number of faces. You don't have to memorize all of these, but there's some that are kind of common, and so that would be like four faces would be a tetrahedron, 5 would be a pentahedron, 6 hexahedron. So these are pretty common: tetra, penta, hexa, heptahedron for 7, octahedron for 8, 9's a little different. Enahedron, not very common. Decahedron for 10. 11 is a hendecahedron, not very common. But then dodecahedron, a lot of these are named the same as like the polygons. Then 14 is a tetradecahedron. 20 is a icosahedron. 24, I'm not sure if I can say it properly, but a icositetrahedron. 32, icosiddodecahedron. So you don't have to memorize those, but do know enhedron. In other words, if it has 40 faces, we'll call it a 40hedron, and so on. But probably the ones tetra, penta, hexa, hepta, octa, deca, you should already know those from the polygons, and maybe dodeca. Those are the ones that I would think that you should be able to remember. Okay. So, name the following polyhedron. Well, it has 4 faces, so this is a tetrahedron. There's also another name for this right here. We haven't talked about this one yet, but this would also be a triangular pyramid. Okay, so we want to name the following polyhedron. So you need to count the number of faces. And this, if you can kind of see, it's kind of like 2 pyramids stacked together that have 4 sides. So this has 8 faces. So this is an octahedron. Okay. So in example 2, they ask us to name the edges and vertices of the following polyhedron. First, I'm going to count the sides. That has 6, or the faces, has 6 faces. So that's a hexahedron. And the edges, or the sides, are these line segments. So we have AE. Sorry about that. We have EH. We have HD. Be sure and put your little line segment line over it. We have, was that I think that was a GC. I can't write them in the spaces. BC, that's a G. But we're just going to go around and name all of these. AB, BF, FG, and HG. So there should be 1, 2, 3, 4, 5. I missed DC. Oh, sorry. You can't read this writing, but you've got the 4 on the bottom, the 4 on the top, and there's the other one, AD. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm missing one. Here it goes. EF. So there should be 12. And then the vertices are just the corners. So A, B, C, D, E, F, G, H. Okay, so I'm not going to write those down, but it's just all of the corners there are the vertices. So here's a formula called Euler's formula that tells us the number or the relationship between the number of faces, vertices, and edges. And here's the formula. Faces plus vertices equals edges plus 2. They want us to apply that to this, let me move it up a little, dodecahedron, which means it has 12 sides. Looks like a soccer ball to me. Sometimes these are hard in this picture to name them all. But, so the faces, let's see, it has 12 faces. So I'm going to put faces plus vertices equals edges plus 2. So we know it has 12 faces. And then the vertices, let's see if we can count them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I think there's another one back there. If you had the ball, it'd be a lot easier to see. So that says 20, which would mean that those weren't edges. I'm sorry, those were vertices. So let me clear. I wrote that in the wrong spot. Sorry, trying to get rid of that 20, and I can't seem to find my eraser. There it is. All right, so now let's try and count the edges. So if that is right, there should be 30 edges. Let's see if we can count those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. There should be one more. It's kind of hard to do in this 3D picture here. But the idea is if you had a solid in front of you, it would be a lot easier than to try and do it from this picture. So let's look at applying the formula here. A polyhedron has 8 vertices and 12 edges. How many faces? So we're going to go back to the formula. F plus faces plus vertices equals edges plus 2. And just fill in. It has, we want to know the faces. So faces plus 8 vertices equals 12 edges plus 2. And then you just solve. Faces plus 8 equals 14. And so if you subtract 14, you get 6. Okay, so faces plus vertices equals edges plus 2. Now we're going to look at cross sections. A cross section in a solid, a cross section is a two-dimensional object seen on the slice plane. And these pictures right here are pretty good. So we have our initial solid here, okay? And so this is a triangular prism, okay? And so in a prism, remember that the sides are always rectangles, and then you name it by the shape of the base. This is why the base here is the two congruent parallel faces. So if you take a cross section horizontally here across the base, it's going to be in the shape of the base. That's why this cross section here is a triangle, because it is taken horizontally from the base. Now if you take a vertical cross section, it's going to be the shape of the side, which in this case is a rectangle. Okay? So name the geometric figure created by the cross section of a cylinder. So I'll do my best to draw a little cylinder here. The bases are circles. And if you remember when we looked at the net of a cylinder, the shape of the lateral surface is actually a rectangle. So I don't know how well I can draw it here, but if you take a cross section this way, it's going to be in the shape of the base, and it's going to be a circle. If you take a cross section out this way, it's going to be in the shape of, that flat surface once the net is built, which is a rectangle. So even though you might appear that it would be curved, it's not going to be curved. It's going to be a rectangle. Okay? So in the quick check below, in the following solid, name the geometric figure created by the cross section parallel to the base. It says bases, but there's only one base because this is a pyramid. And so the base is a square. So if you take a cross section out this way, it will be a square. It's going to be in the shape of the base. If we take a cross section out the other way, again, I wish I had could show you some figures here a little bit better, but it's going to be in the shape of the side, which is a triangle. So in a pyramid, and hopefully they'll have a better picture here for you, but when you take a cross section out vertically, it will be in the shape of the side there, which is a triangle. Okay, so find the area of the plane figure formed by the cross section of the cube. Now you see the way that they have put this cross section through. It goes from the diagonal. So what they're talking about is this part that's shaded. So this right here, which is a rectangle, and we can see that this side is 6. A rectangle is length times width, so we need the length right here. And if you can see, that goes through the diagonal of this square. And so if it's a square and all the sides are 6, we would do a squared plus b squared equals c squared. And this is a 45, 45, 90 triangle. So this would be 6 to the square root of 2. So it's just going to be 6 times 6 to the square root of 2, or 36 to the square root of 2, is the area of the cross section seen there going through the diagonal of that cube. Okay, and one more, I think. Okay, so here we have a cross section, and so here's a better picture where you can see that the cross section in this cylinder is actually a rectangle. So we need length times width, and here they show us that the length, because it goes from the top to bottom, is 40. So what we need is this right here. And they give us the dimensions right here and here. Okay, so I'm going to draw that triangle. Okay, this is a right triangle. And so they show that this is 15, and then they show us that this right here is 12. So you just have to do Pythagorean theorem to find this length right here, which is